Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD transfer analysis through a surface condenser using SolidWorks 2022. This is the model you can see. For understanding the model in a better way, let us have a segmented view of this model. We can cut it from front plane. Let us see what is the inside. Let us understand the working principle of this one. Inside this surface condenser, from top entry, this is connected with the steam outlet from the power plant. So this is the entry of steam, and you can see at this location and at this location, both left hand side and right hand side, we are having two baffles. These two baffles are separating steam from the left hand side and right hand side, and this is the exit of steam condensate, and this water at high temperature is directly fed to the boiler, and this is actually an attachment. To have a free flow of steam inside this chamber, we need to extract air from this one, and air will be extracted from this location. In this analysis, we didn't show any kind of air. We have considered that inside this one no air is there, right? So we have shown this one to show that this is the location of pump from which we are extracting air inside. In this analysis, we will not show the existence of air, and we'll maintain zero air inside this surface condenser. And this one is the location of cold water entry, and at this location we are having some kind of baffles. It is separating the top part and the bottom part. From here we will provide cold water at a temperature of 10 degrees centigrade. It will pass from this one and it will go through these tubes. It is a double pass tubes, and again at the left hand side it will be bent, and finally again it will come along this path in horizontal tubes. So this is the entry of cold water at a temperature of 10 degrees centigrade. It will pass through these tubes and finally it will come out from this top exit in the form of a bent U-tube. And as we are providing hot steam from the top side, so there will not be any kind of direct mixing of hot steam and cold water. By convection, steam will lose heat, and at the bottom side we will have steam condensate. That will be water at a higher temperature, and that will be directly fed into the boiler. And here at this location, the cold water will be heated up by getting some amount of heat from steam. So at this location we'll get high temperature water. And in this case, it is better to say that generally in this case the temperature of rise of cold water should be within the range of 10 degrees centigrade. If the cold water temperature difference is more than 10 degrees centigrade, in that case we can increase the volume of the surface condenser, right? So this is completely understood. Now let us start our simulation. For starting this flow simulation environment, it will be started with the flow simulation, and finally to initiate the environment we should start with wizard. And we're keeping the name of the project as project 3 because already two different projects we have done with same data. So we're considering this one as project 3, and unit system we'll consider as SI. And from here we'll consider temperature as degrees Celsius and pressure will be in bar. Next to that, it will be an internal analysis, and from physical features it will be fluid flow with conduction, and definitely gravity will be involved, and direction of gravity will be Y as shown by the green arrow in the upward direction. So along Y gravity will be minus 9.81 meter per second square, and along Z it will be 0. Next to that, we need to select a defined fluids. Actually in this case we should have three defined fluids: water, air and steam. Air we are not considering because inside this steam we need to provide vacuum pressure or zero pressure. That's why we are not considering any kind of air inside this surface condenser. So we'll be considering only water and steam. So from here liquid it will be water, and we need to consider steam also. Next to that, we need to select different materials for this shell and tubes. We can see the tubes are made up of copper. So from here we can select metals and copper, and the remaining materials will be selected during application of boundary conditions. Next to that, we are considering default out-of-wall thermal conditions and roughness, and finally we can select that pressure should be 1.01325 bar and temperature will be 10 degrees centigrade, and solid parameters also it will be 10 degrees centigrade. Let us finish this. You can see this is the computational domain. All the leads are provided, so it will be closed volume. It is done. Now you can hide this domain and go for different types of fluid subdomains and boundary conditions. So hide the domain, and for providing fluid subdomains we can have a segmented view of this model. So we'll cut the model from front plane and insert fluid subdomain. First of all, we provide water at a temperature of 10 degrees centigrade from the down location here. So you can see this is the cold water domain. You can see temperature is 10 degrees centigrade, right? Then check. Next to that, we need to provide fluid subdomain for steam. Fluid subdomain, insert fluid subdomain. It will be steam, so you can change it from here itself. Steam at a temperature of 100 degrees centigrade. That will pass from the top entry here. So this is the fluid domain for steam at a temperature of 100 degrees centigrade. Both the fluid subdomains are defined. Again, we are repeating that we are not considering any kind of air in this case, and we're extracting air from this location, right? Fine. Next to that, we need to define materials. So insert solid materials. It will be copper. So predefined metals, copper, and we can select this copper from the geometry itself, solid body, and in between we should select the shift button. All the tubes are selected, and as the material we are providing copper to that one. Then check. Copper material is provided for the tubes. Next to that, we need to provide steel 321 for the shells and the remaining materials. Insert solid materials and predefined alloys. It will be stainless steel 321, and let us select the remaining materials from here. It will be select the different parts separately. When the leads are also made up of stainless steel, all the parts are selected, and these parts are made up of stainless steel 321. Green check. All the materials are defined. Next to that, we need to apply boundary conditions. Insert boundary condition, and we need to provide water from the down entry at a pressure of 101.325 Pascal or 1.032 bar, and in this case we're considering inlet velocity of cold water to be 0.5 meter per second, and thermodynamic parameters it will be 10 degrees centigrade, right? Let us select that location. Selected. Then check. One boundary condition is applied. Now we have to provide steam from the top entry. Insert boundary condition. It will be inlet velocity of steam from the top entry, and thermodynamic parameters it will be steam at a pressure of 1.01325 bar and temperature 100 degrees centigrade, and in this case we are considering velocity to be 0.01 meter per second. Then check, and two more boundary conditions are needed. Those are the exits of steam and cold water. So insert boundary condition, it will be atmospheric pressure or environmental pressure at the exit of cold water. First, let us select that location. Selected. You see environmental pressure is 1.0325 bar and temperature is 10 degrees centigrade at the exit of cold water. Print check. Finally, you need to provide environmental pressure at the exit of steam, where steam condensate will be collected. Water at high temperature will be collected. This is the location. So insert boundary condition. It will be environmental pressure at the exit of steam. Green check. All the boundary conditions are applied. Now what can you do is we can rename these things. Let us rename things from fluid subdomains. First one is the fluid domain of cold water. We can rename this one as cold water subdomain. Cold water domain, this one. Second fluid subdomain, we can define this one as steam domain. Similarly for the boundary conditions also. First one is the inlet velocity of cold water. Second one is the inlet velocity of steam. This is not required, but we are making this one for better understanding. Inlet velocity of steam and these two environmental pressures. First one is the environmental pressure at cold water exit, and the final one is the environmental pressure at steam exit, or you can say at steam condensate. All the boundary conditions are applied. Next to that, we need to find goals. In this case, you can find a lot of goals, but our main aim should be to have temperature at the exit locations. So it will be surface goals. Insert surface goals. And first of all, we'll select average temperature of fluid at the exit of steam. And at the same time, we need to have average temperature at the exit of cold water also. Selected. And we need to have separate goals for each of them. Green check. And we can rename these things as first one as average temperature of steam at exit, or you can say average temperature at steam exit. And the second one is average temperature at water exit. So both the goals are defined. Next to that, we need to find out equation goal. That means we need to find effectiveness of the surface condenser. It will be LMTD, or you can say logarithmic mean temperature difference. That will be an equation goal. So insert equation goal, and it will be initiated with the brackets, and the parameters for this one will be obtained from the boundary conditions and from the goals. Let us insert boundary condition. It will be obtained from inlet velocity of steam, that is temperature at steam inlet, that is 100 degrees centigrade, minus temperature at cold water inlet, that is 10 degrees centigrade, then bracket closed, minus initiate bracket. Then you need to find out the surface goals, that is average temperature at steam exit minus average temperature at water exit, bracket closed, and the whole expression can be taken within another set of brackets. We can initiate another bracket at the entry also, then divided by ln of, you can copy the whole parameter what is there in the left hand side, and that can be pasted after ln. And here in this case, at this location, you can provide this minus as division. Done. Green check. Our equation goal is obtained. We can rename this one as LMTD. It is a difference in temperature of inlet of steam and inlet of cold water minus a difference in temperature at the exit of steam and at the exit of cold water divided by ln of difference in temperature at inlet of steam and inlet of cold water divided by difference in temperature at the exit of steam and exit of cold water, right? So all the goals are defined. Next we can run it. We have already run this setup with the same data in project 2, so we can see the results from project 2, right? First of all, we want to see cut plots of pressure and temperature, etc. from front plane. For that, we can make the model completely transparent, or we can have a segmented view of this model, right? So insert cut plots, and we will see temperature of feed, and that could be viewed from front plane. Brain check. This is the temperature distribution through the front plane, and it will be better to see in the form of an animation. Let us play it. It is showing through the shell, but inside the tube also it is showing very little amount. Let us see it from front plane in a better way. Let us see pressure distribution first. Instead of temperature of fluid, we can see pressure distribution from front plane. You see pressure remains almost constant throughout. It is given by blue color. Next to that, we will see this temperature and pressure from right plane also. So cut plot 2, clear and hide. And what we'll do is cut plot 2, edit definition, and we'll see this from right plane. Instead of pressure, it will be temperature of feed. And we'll see it from right plane. We can drag it, brain check, and we can orient this model. We want to see this one from right plane. Let us see these things, that in this case you can see the flow of cool water through these pipes in a better way, right? So let us play it. Instead of doing that one, we can see, we can make the model completely transparent. Then you can view the different cut plots of pressure and temperature from different planes, right? You can see the flow through the tubes also. Let us clear and hide this one. Next to that, we'll see surface plots. Insert surface plots, and we'll see through all faces, and it will be temperature of fluid. Brain check. At the boundary of this shell, you can see temperature distribution. Next to that, we'll see the goal plots. Insert goal plots, and we want to transfer it to Excel. Before that, we need to select all the goals, and we can export it to Excel. First one is average temperature of water at exit. We can see Initially, average temperature at the exit of cold water was 10 degrees centigrade, and here after 366 numbers of iteration, we can see average temperature at the exit of cold water is 24.99 degrees centigrade, that is approximately 25 degrees centigrade. Next one is average temperature at exit of steam. Initially, average temperature at the exit of steam was 100 degrees centigrade, and you can see after 366 numbers of iterations, we can find that average temperature at the exit of steam is actually 97.41 degrees centigrade. And you can see here that average temperature at the exit was constant for some time, from iteration number 120 to 270 iterations. Temperature of steam was constant. That means during that time, phase change of steam was occurring, right? So from steam at 100 degrees centigrade to water at 100 degrees centigrade, it took a huge amount of time, and a huge amount of heat was extracted during that time, and finally it has come down from steam at 100 degrees centigrade to water at 100 degrees centigrade, and then temperature of steam was reduced to 97.41 degrees centigrade, right? So it is not just a decrease in temperature of 3 degrees centigrade, because huge amount of heat was extracted from converting heat from steam at 100 degrees centigrade to water at 100 degrees centigrade. That was in the form of latent heat, right? With this one, we'll conclude the today's analysis. Instead of stopping it here, you can go for some kind of parametric study by varying different input parameters. The input parameters may be the temperature of cold water, or you can say the mass flow rate of cold water, and finally you can go for some kind of optimization based on your requirement, right? So thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.